Hello everybody, I again welcome you all to the second session of mechanical measurements of Unit 6 of mechanical measurements. This is Praveen Kumar, lecturer, Government Polytechnic, Karate. So, in the last session, we have learnt about what is interchangeability and what is selective assembly. I just want to have a recap on the definitions of interchangeability and selective assembly. In the previous session, we have already learned about the definition, some of the uses of interchangeability and definition of selective assembly and uses of selective assembly. Let me just recap on the definition of what is interchangeability and what is selective assembly. So firstly, what is interchangeable assembly? It is when a large number of components are to be produced, then it will not be economical to produce both the mating components by the same operator. In addition to the economy, it is also essential to produce the components within the minimum possible time. This is only possible by mass production system. In mass production system, there is a division of labor. The components are produced in one or more batches by different operators on different machines. Under such conditions, in order to assemble the mating components with a desired fit, a strict control is exercised and the parts are manufactured with specified tolerance limits. When a system of this kind is used, any one component selected at random will assemble correctly with any other mating component that too selected at random. This system is called interchangeable assembly. The manufacture of components under such conditions is called interchangeable manufacture. Production on an interchangeable basis results in increased output with a corresponding reduction in manufacturing cost. So this is about interchangeable assembly, which we learned in the previous session. Okay, now we will know what is selective assembly. It is sometimes found that it is not economical to manufacture parts to the required degree of accuracy so as to make them interchangeable. The consumer not only wants quality and precision, trouble-free products, but also he wants them at economical prices. Often, special cases of accuracy and uniformity arise which might not be satisfied by the certainty at fits given under fully interchangeable system. For example, if a part of its low limit is assembled with mating part at high limit, the fit so obtained may not fully satisfy the functional requirements of the assembly. Complete interchangeability in the above cases can be obtained at some extra cost in inspection and material handling by using selective assembly, whereby parts manufactured to rather wider tolerances. In selective assembly, the components produced are classified into groups according to their sizes by automatic gauging. This is done for both mating parts, holes and shafts, and only matched groups of mating parts are assembled. It results in complete protection against defective assemblies and reduces matching cost since the parts were produced with wider tolerances. So this is about selective assembly. So in this session, we will learn about some of the basic definitions of limits, fits and tolerances, and also we will see the graphical representations of all the definitions. Now you see one graphical representation of different terms used in limits, fits and tolerances. Now on the screen you are seeing a graphical representation which tells you about some of the terms used in limits, fits and tolerances. That is, we have shaft, we have hole, we have zero light, and we have minimum diameter, maximum diameter and basic sizes, and some of the deviations and tolerances. I'll let you know the brief definitions of all the terms, right? And the first one is the basic size. It is defined as a theoretical size of a part derived from the design after rounding off to the nearest whole number. The tolerances are always specified to the basic size. And nominal size. It is a size of the component by which it is referred to as a matter of convenience. Actual size. It is defined as the size actually obtained by machining. It is found by actual measurement using measuring instruments. And limits. It is the two extreme permissible sizes between which the actual size lies are called limits. The maximum and the minimum permissible sizes within which the actual size of a component lies is called limits. Now we will know what is maximum limit. Maximum limit is defined as the maximum permissible size for a given basic size. What is minimum limit? It is defined as the minimum permissible size for a given basic size. And what is tolerance? Tolerance is defined as amount of variation permitted to a basic size. So what is a zero line? It is the line with respect to which the position of the tolerance zones are shown. Now we know what is deviation. Deviation, it is the algebraic difference between the actual size, limit size, either maximum or minimum, and the corresponding basic size. So what is upper deviation? Upper deviation is the algebraic difference between the maximum limit of size and the corresponding basic size. It is denoted by letters ES, capital ES for a hole and small es for a shaft. What is lower deviation? It is the algebraic difference between the minimum limit of size and the corresponding basic size. It is denoted by the letters capital EI for a hole and small letters EI for a shaft. So what is fundamental deviation? It is a deviation either upper or lower deviation which is nearest to the zero line for either a hole or a shaft. It fixes the position of the tolerance zone in relation to the zero line. So what is actual deviation? It is the algebraic difference between the actual measured size and the corresponding basic size. So now we know what is an allowance. Allowance is an intentional difference between the hole dimensions and shaft dimensions for any type of fit. So what is a basic shaft? It is a shaft whose upper deviation is 0. That is, the maximum limit of shaft coincides with the nominal size, that is 0 line. And what is a basic hole? It is a hole whose lower deviation is 0. That is, the minimum limit of hole coincides with the nominal size, that is 0 line. So now we have different definitions related to the terms that are used in limits, fits and tolerances. For your reference, all the definitions are put in the slide. Just go through them for some time. Now we will have a graphical representation of limits and tolerances. This is the graphical illustration which gives you idea on what is the basic size, what is the maximum limit, what is the minimum limit, and what is tolerance. I'll just read out some of the definitions related to the limits and tolerances. So what is a limit? What are the limits? These are the two extreme permissible sizes between which the actual size lies are called limits. The maximum and minimum permissible sizes within which the actual size of a component lies is called limits. So what is maximum limit? It is defined as the maximum permissible size for a given basic size. What is minimum limit? It is defined as the minimum permissible size for a given basic size. Same way, what is a tolerance? Tolerance is defined as the amount of variation permitted to a basic size. So these definitions are illustrated in the picture as shown. Now we have a video which will give you an idea of what exactly is limits and tolerances. Just go through the video.
Let me know the difference between limits, fit and tolerance. Limit is the maximum and minimum allowances from the basic size. It is called as limit. The dimensions of manufactured parts can only be made to lie between the maximum and minimum limits. That we have an example here. Diameter of the shaft is 25 mm and limits are plus or minus 0.15. The maximum limit is 21.15 and minimum limit is 24.85. The maximum allowances from upper side to lower side. This is called limits. We see the difference between fits and tolerance. Fits are the relative motion exists between the mating parts. Here, soft and whole are example for these fits. And tolerance are the difference between the maximum and minimum limits. Here we can see that the tolerance is upper 0.15, lower 0.15. Totally 0.3 is the tolerance for this shaft. Let me see the example here. This is the best example for the fit. Fits can be classified into three types: clearance fit, transition fit and interference fit. Here the shaft size is less than the hole size. Lot of clearance is there. It is clearance fit. Next one is transition fit. Shaft and hole diameters are same. That type of fits transition fit. Interference fit. The shaft diameter is bigger than the hole diameter. This is transition fit. Let we see the tolerance here. This is the shaft. This black color indicates the allowances, upper limit and lower limit. Let me say take the hole as example here. This is the basic size and upper limit and lower limit. Thank you.
Okay, now I hope you have understood the definitions of all the terms related to the limits, fits and tolerances. Okay, so now we'll have, that is it for this particular session. Okay, and further we'll be learning about different things in the next session. Thank you.